lecture, I will be dealing with a problem on the classical mechanics, on the classical physics, which will be simpler in nature. This is just to give you an intuition about how to apply the laws of Newtonian mechanics onto the physical problems. So in this very problem, consider an example. If we have a particle moving along a parametric curve is given as R equal A times cosine of omega t along the x-axis plus, this is the unit vector along the x-axis, plus b sine of theta, that is sine of omega t, along the y-axis, that is j hat, this is the unit vector along the y-axis. This is the parametric curve, okay? Parametric curve. Parametric means there are different kinds of parameters, that's a, omega, upon which the motion of the particle depends, and these are constants. Actually, parametric curve is given as this R, and a, b, omega, these are all constants of motion, okay, constants. And I and j are the Cartesian unit vectors. You already know them. These are the Cartesian unit vectors along x-axis and y-axis respectively. If there is a k component also, that is the component present along the z-axis also, that means the motion would have been in the 3 dimensions, but here it is only along to the 2 coordinates. That means the motion is 2-dimensional only. So in that case we have to find the force and comment upon the type of force, which type of force is acting onto this very particle if it is moving along the parametric curve this. So motion is given along this very curve. We have to calculate its force and discuss what kind of force it is. So first of all, we will get force by applying second law of motion, but for that we have to calculate acceleration, because acceleration gives, then upon applying the second law of motion we can deduce the force acting onto this body. So for that we have, say for example, this is a cosine and a sine term, so that means the parametric curve will be something like this. It can be any shape which can be seen upon applying this very thing in software, where you can deduce the actual curve. But here we can roughly say that it will be something like this. So consider a particle here, it follows a path like this from time t to t prime, okay? So this will be the path which is traversed by that very particle. So the position vector at any instant of time, R is given by a cosine of omega t I plus b sine of omega t j. This is the position vector of that very point particle along the parametric curve, position vector, okay? So to calculate the acceleration we need to double differentiate this very position vector with respect to time. So differentiating first with respect to time, we will get r dot, that is dr by dt, will be equal to, differentiate this, a is constant, omega is constant, so a kept it is as it is, keeping this as constant. Cosine of omega t, differentiation of cosine of omega t is sine, because differentiation of cos is minus sine omega t, and there is an extra term omega, it will come outside, so differentiation will be minus times omega sine omega t, and differentiation of sine omega t will be equal to plus, because differentiation of sine is plus times cos, that is cosine of omega t with an extra term omega coming out. So we will write it down as cosine of omega t differentiation will be omega sine omega t with a minus sign, okay, along the y-axis, plus b omega cosine of omega t g, because differentiation of sine is cos plus times. Now this will give the velocity along the curve, okay, but we need the acceleration. So for acceleration, differentiating this very equation again, differentiating again with respect to time. So that means d2r by dt squared, that is the r double dot, that is the acceleration, d2r by dt squared. So we have to differentiate this very equation now again with respect to time. So differentiation of sine is cosine of omega t with an extra term omega, and differentiation of cosine of omega t is minus times, here it will be minus times now, minus times sine omega t with an extra term omega, and keeping b is constant, omega constant, a is constant, these will be all constants outside. So we will get minus here, sine omega t differentiation is cos plus cos, so that means we will get minus times a omega cosine of omega t, sine differentiation is cosine omega t with an extra term here omega, already one omega is there, and extra term omega here, it comes out to be omega squared, okay, plus here plus b omega differentiation of, now again with respect to time, differentiating this, cosine of omega t differentiation is minus times sine omega t with an extra term omega, extra term omega gets multiplied to this, it will be omega squared, but minus sine omega t, this will be along y-axis and this will be along j-axis. Fine, so we will get here, we'll get all double dot will be equal to minus here, keep it outside, omega square here, omega squared here, keep this also outside. What we'll get inside the brackets, it's a here, cosine omega t I along the x-axis, plus, because minus is outside, omega squared is outside, we'll get plus b sine omega t along j-axis. So this will be the acceleration, but if you see onto this, a cosine of omega t, b sine of omega, it is the position vector back, so r double dot will be equal to minus times omega square, this very stuff, and this is r, so we can write it down as acceleration, that is r double dot will be equal to minus times omega square multiplied by this, and this is the position vector itself, that's omega square r, okay. So this will be the acceleration of the body which is moving along some curve with r equal to a cosine of omega t I plus b sine of omega t j. So this, if this is the parametric equation, the particle is moving along this very curve, so for that